So in the previous lecture, we discussed about differential amplifiers, and we saw how to compute the differential gain of a differential amplifier and the common mode gain of a differential amplifier, and finally a very important metric for a differential amplifier, which you said is ACM-DM. The differential gain is given by, so if you have a differential amplifier, so I am representing by this symbol, input here in both the circuits is differential, output is also differential. Then we said AD here represents, so if VOD is the output differential voltage, VID is the input differential voltage, then we said AD is given by VOD by VID. ACM, the common mode gain, is measured by short circuiting the inputs and then taking the average of the two outputs. So this is VO plus, VO minus, and so it is VO plus VO minus by 2. We said by arguments of symmetry, we can argue that both V0 and VO plus and VO minus will have same variations. Okay, so that should make sense. You just look at any one output's response, that should make sense. That will give you the common mode gain. But anyways, the general procedure was that we took the average of the two and we called it VOCM, and VICM is the input signal average, or the same signal applied to both the terminals. So this is how we define ACM. Finally, we defined a very important parameter called ACM-DM. ACM-DM is measured, you apply a common input, so you're going to apply VICM, same inputs for both the inputs, and then what are you going to do is that you're going to take the output differentially. But you're applying same input. So that's called ACM-DM. And what did we say for an ideal differential amplifier? What will be the value of ACM-DM? Purely symmetric circuit. What should be the value of ACM-DM? 0, right? That should be perfectly 0. That's it. And we took two examples shown here, and we calculated all these three parameters. And in the previous lecture, we introduced the idea of half circuit. We said that if you see an actual differential amplifier, when we were trying to find out the voltage gain or the common mode differential and common mode voltage gains, we were analyzing both half of the circuits, and since both half of the circuits are identical, we didn't really need to analyze both the halves. Can we just analyze one half of the circuit and get all these parameters, differential gain and common mode gain? Can we just analyze one half and get these parameters? So that's when we introduced the idea of half circuit. We said there are two different half circuits. You have one half circuit for differential circuits, then for differential gain, and one half circuit for common mode gain. Okay, so we had two different half circuits. So first, what was the method by which we drew the half circuit? So we said any circuit differential amplifier, split it into equal identical circuits, and then draw an axis of symmetry. If you draw an axis of symmetry, when I'm drawing a differential half circuit, what will happen? Wherever the axis of symmetry intersects the circuit, what will be the potential at that point? When a differential half circuit, whenever the axis of symmetry intersects at any point, it is 0, right? The potential at that point will be 0. So, and we said that makes intuitive sense because it's a fully differential circuit. If it's a fully differential circuit, since the circuit is symmetric on either sides, and if I'm applying delta V and minus delta V, this node is going to come to differential ground. Okay, so that's what we argued. Similarly, if you take the circuit on the right here, I'm going to again draw an axis of symmetry, and I'll actually replace this with two current sources of value I by 2 and I by 2. And this is the axis of symmetry here. So then this point will come to AC ground, this point will also come to AC ground, differential AC ground for differential half circuit. So if R is the gain here, R is the resistance here, GM is the transconductance, same GM is the transconductance and R is the resistance here. What is the differential gain for both the circuits? So this node comes to ground. So if this node comes to ground, the circuit differential half circuit is same for both. It is GM times R. right? We said that the differential gain is GM times R. Okay, so that's your differential gain for both the circuits. Both the circuits, even though this is voltage biased and this is current biased, the differential gain is same for both the circuits. Okay, so that finishes our discussion on differential half circuits and how to find differential gain from a differential half circuit. The next procedure is to find common mode gain for these circuits. So when I'm finding the common mode gain, how do I do it? Again, go with the same approach, draw an axis of symmetry. Draw an axis of symmetry here as well. What should you do in common mode circuit as opposed to differential? What is the only difference? Wherever the axis intersects the point, wherever it intersects the circuit, the differential circuit, open circuit those nodes. So you'll have to open circuit these nodes, and anyway, supply is open circuit. So between the two, it has two different supplies. I've open circuited this node as well. So this is how the circuit behaves for common mode inputs. Now, if you see, the common mode half circuit is very different for both the circuits. Even though differentially both the circuits look the same, for when I apply common mode inputs, both the circuits are very different. So let's take the first circuit. In the first circuit, if I apply the common mode input, what will happen? The source will come to AC ground. Since I have to only analyze one half of the circuit, so the voltage gain here will be GM times R. This is your ACM with a minus sign. Now what is ACM in this circuit? I have to analyze only one half here. What is the ACM in this circuit? So look at this. This is biased using a constant current source. What does it tell you? Intuitively, if you see, if I'm biasing it using a constant current source, it is telling me that the drain current of this MOSFET is always fixed. The drain current of this MOSFET is always fixed. So if the drain current is always fixed, what is the small signal variation in the drain current? So I'm asking a simple question. If the drain current is fixed, small signal variation has to be zero, right? If the drain current is always fixed, then the small signal variation is zero. If the small signal variation in drain current is zero, then the small signal variation in the drain voltage will also be zero because it's resistively terminated. I mean, you have a resistance at the drain terminal. So the small signal voltage drop across the drain will also be zero. That's it. So you can directly say ACM is zero for this circuit. Okay, so that's how we analyzed it properly, rigorously by brute force approach as well, and then we drew a differential half circuit, analyzed it as well. And I said there is a method too for finding differential half circuit. So you can draw a line along this axis of symmetry and fold this circuit and overlay on top of it. Even that is other way of analyzing common mode half circuits, drawing common mode half circuit, and from that deriving common mode gains. Okay, so this is the procedure, and we saw how to calculate the common mode and differential gains for differential amplifiers. Now we'll take some examples and we'll see how to calculate both the differential and common mode gains. So let's start with this circuit. So this is the circuit that's given to you. So let me draw it first here. So you have the same differential pair with a resistor in between, a current source with a finite output resistance. I'm going to call it ROC. So this is R, and R. The first step whenever we are drawing a differential half circuit is to split the circuit into two halves. So first we need to split the resistor here into two halves. Okay, and previously we said this, you have a current of I here. So this, if it's purely symmetric, then at DC the current will split into two halves. So this will be I by 2 and this will be I by 2. So I can model this current source as I by 2 here and I by 2 here. Now see, it's a purely differential circuit. So we said this resistance ROC will also be modeled across the two current sources. But what should be the value of the resistance here? Will it be ROC or something else? Because you have to ensure that the parallel equivalent of both should be equal to ROC. So they both are in parallel, so it has to be 2 ROC. Okay, it will be 2 ROC. Now, once we have drawn that, the next step involves drawing the axis of symmetry. So I'm going to draw this axis of symmetry. So when I'm drawing axis of symmetry here, what happens here? This node is already shorted here. So this node will come to AC ground and this node will come to AC ground. So does this resistor R matter? Does this resistor R matter in your gain? In differential circuit. I'm talking about differential gain. Does this R matter in differential circuit? No, right? Because this node comes to AC ground. The other end is also at AC ground. So the current through the resistor is 0. So the differential half circuit reduces to something like this. Source will be at AC ground. You have a resistance of value R by 2 here, and this is R. Okay. Now, what will be the differential gain for this circuit? You just have to find the common mode gain. The differential gain is same as that. So what will be, sorry, you should find the half circuit gain, that's same as differential gain. So it is GMR by 3. Okay. The sign is important. Sign, you have to look at your circuit. You have to look at the circuit to write the sign. I told you guys in differential pairs, you have to look at the circuit to write the sign. Half circuit will not give you the sign information, it will only give you the gain value. Okay, it will just directly give you the gain value, which is GMR by 3. You have to look at where the output is taken. So let's assume this is VI plus, this is VI minus. This I'm taking it as positive as with respect to the input. So then if I denote this as VO plus and this as VO minus, what will be the value of the gain? Will it be negative or positive? See, this is VO plus, this is VI plus. Gain is positive, right? So the gain is positive if you take it this way. If I flip the terminals, if I make this as VO plus and this as VO minus, then the gain will be negative. So we said that's an added advantage of differential pair. If you want a negative gain, you just have to flip the output terminals. Now, the next important thing which I'm going to do here is to find the common mode half circuit, the common mode half circuit and the common mode gain of this circuit itself. To derive the common mode half circuit, so first again, I'll have to draw the axis of symmetry. You can follow either of the approaches, you will get the same answers. What should you do when you draw the axis of symmetry is that you should open circuit the central node. So you have open circuit this node here, and you should also open circuit the point where the resistors interact. This is open and supply. Anyways, I'm going to split it into 2. So this becomes your common mode half circuit. Now we can do the small signal analysis. VDD is at AC ground, open circuit the current source. You'll get the circuit here. So this is 2 ROC. This is R here, and the resistance here is actually R by, it is R by 2 itself. So you can just consider one half of the circuit and completely ignore the other half, right? So to draw the half circuit, we said you should do this. Now, what do you think will be the common mode gain of this circuit? Will this resistance R by 2 matter? The current flowing through this is 0, right? If the current flowing through this is 0, resistance voltage drop is 0, so I can ignore this resistance. So this node voltage here is VOCM. Now, what will be the gain of this circuit? Let's assume R naught is infinity or lambda is 0. What will be the gain of this circuit, voltage gain of this circuit? Yes. So one of you wrote it right. So what is the gain of this circuit? So the moment you add a source resistance to ROC, the GM reduces significantly. Okay. There are 2 approaches to write this. I said the total drain resistance divided by the total source resistance, which is 1 by GM plus 2 ROC. You can write it this way. Or you can also say that, if you recall, I've discussed once that let's say I add a resistance R to the source. Let me call it ROC to the source or 2 ROC to the source. The transconductance previously, when we didn't have 2 ROC, here in this case it was GM times VI. Now if you see a small fraction of GM appears across, VI appears across VGS. So therefore this current will be GM upon 1 plus 2 GM ROC times VI. Okay, so GM reduces. So this term we called it as effective GM. The GM reduces. So it's an open book, so you can keep these results handy, okay, for your exam, for your quiz. So you get GM by 1 plus 2 GM ROC. So therefore, the gain will simply be this transconductance times the current resistance at the drain. So that will be R. So this is your common mode gain with a minus sign, but if you ask you the magnitude, it will only be this much. Okay. So now if you see this
Sir,
circuit, yes.
sir, in the above diagram, in the lowest edge, the voltage from the left half and voltage from the right half will be equal, right? So there will be no current in ROC.
No current between these two terminals. But this voltage is finite, right? See, this is not a differential circuit, this is common mode. So I'm applying VICM here and VICM here, both are same. If you apply both VICM and VICM, then these two nodes will, the source node will increase by the same potential. Source node won't come to AC ground. Only when you
Oh,
apply a
okay.
differential input, source will come to AC ground. Right now, it will be some voltage. See, this potential and this potential will be same. These two are equipotential, so there won't be any current between these two terminals. This will be zero, but current can flow here to ground. It can flow. It's a common mode input, right? So both this gate voltage and this this node voltage and this node voltage will be same. Okay. Okay. So now we just derived an expression. So now if you see, as a designer, if you want to reduce the common mode gain, what will you do to this current source? How will you choose what kind of a current source will you prefer? If you want to reduce your common mode gain, look at this expression. What can you do? See, generally GM is decided by your this increase ROC, right? You'll keep increasing your output resistance. Or see, look at this GMR divided by 1 plus 2 GM ROC upon R into R. So I'll write it this way. So this expression can then be written as the differential gain AD upon 1 plus 2 AD into ROC upon R. Or I'll take 2 here, so 2 ROC upon R. You get an expression like this. So when you look at this here, generally once you fix your differential gain, if you want to have a very low common mode gain, then you have to ensure that your 2 ROC is much greater than R. Okay, you have to ensure that your 2 ROC is much greater than R. If you ensure that, then the gain reduces to R by 2 ROC. Does that make sense to you guys? If I ensure R is 2 ROC is much greater than R, okay, so this term will be much greater than 1, so I can ignore it. So AD and AD will cancel out, so you will get R upon 2 ROC. So if you want to reduce your common mode gain, then choose ROC as high as possible. So if let's say I can't get a good resistance using a simple current source, then to increase output resistance, what should I do? If I am not able to get that resistance using a simple current source, what should I do to increase the output resistance? A cascode current source, right? You should go for a cascode current source that's going to increase your ROC. That's it. So that finishes ACM for this circuit. What about ACM DM? What is the value of ACM DM for this circuit? 0, right? It's purely a differential circuit, so therefore it is 0. It's a purely differential circuit still, so there's no asymmetry in the circuit, so still it is 0. Now, very briefly, I'll just discuss of the other approach for finding the gain as well. In common mode half circuits, we said there are 2 approaches to draw it. So, yeah. So what should you do here in the other approach is that around this node, you're going to fold this whole circuit. So your transistors W by L will become 2W, current is going to be 2I, and this, see, now that you're adding this whole circuit in parallel with this arm, your 2 ROC in parallel with 2 ROC will become ROC here. And the resistance here, what will be the value of the drain resistance? Because I'm overlaying this resistor on top of this. Drain resistance will become R by 2. So your transconductance GM will become 2GM. So now can you tell me what will be the expression for the common mode gain using this? So you will get 2GM times R by 2, that's your drain resistance, divided by 1 plus 2GM into ROC. Okay, yes. So one of you said there not be an R by 4 here? Yes, there will be an R by 4. So for example, if you see this resistor, around this node we are folding the circuit, so this node will be connected to this. So you will get R by 4 here as well. But that R by 4 won't matter because the current flowing through this is 0. So that's, it doesn't really matter. So that's why we ignored R by 4 and wrote it as VOCM. The common mode gain here is 2GM into R by 2 by 1 plus 2GM into ROC. And if you see, you get the same expression as you got before. So this 2GM into R by 2 will just be GMR divided by 1 plus 2GM into ROC. Yeah, see, generally when we ask common mode gain, we'll not care about polarity. You can just express its magnitude. Okay, that's it. Generally, gain will be negative for a common source differential pair. It will be, because you are using a common source differential pair, it will be negative. If I use a common gate differential pair, it will be positive. That's it. Yeah. Differential gain can be both positive or negative. That you have to look at the circuit and figure that out. Common mode depends on the architecture. It can be positive, and yeah, that's it. But as I said, the more important thing is the magnitude itself. The magnitude of the gain is more important to us. Okay, so that completes our discussion on common mode gains. So we'll take a few examples. So there are 3 circuits given here. So we'll try to find out the differential gain and the common mode gain for these 3 circuits. So let's start with the first circuit. So your goal, the moment you see a circuit of this type, automatically you should start drawing a half circuit. So in the half circuit, split the current source as 2 current sources of value ISS by 2. So this is ISS by 2, and you'd have this circuit this way. So now if you see, there is an axis of symmetry here. Okay, so this node will come to AC ground. This will also be at AC ground, differential ground. So once you draw the half circuit and find the differential grounds in the circuit, then you can draw the small signal AC model. The small signal AC model is this here. So you have a diode connected MOSFET to ground from the output terminal, NMOS diode connected MOSFET. So what will be the gain of this circuit? So the upper transistor is 3 and 1. So let's assume this is GM3. Let's ignore R03 for the time being. So this is GM1. The gain will simply be GM1 by GM3. Right? The looking up impedance is 1 by GM3, and the gain is GM1 by GM3. If you have to take R0 into consideration, what do you think will be the change in the gain? So GM1 remains the same. That's the short circuit transconductance. If you take R0 into consideration, what do you think will be the difference? What will be the looking up impedance and looking down impedance? The looking up impedance is going to be 1 by GM3 parallel R03. Then there will also be a resistance looking down, R01, that will also be in parallel. So this will be your total gain expression. So this is your differential gain. So what is the common mode gain for the circuit? If you are asked to find the common mode gain, I'm going to draw the half circuit this way. As soon as I'm drawing the half circuit, I'll have to open circuit this node, open circuit this node. So now quickly tell me what will be the common mode gain by looking at this half. So if I apply VICM here, what's going to be the common mode gain? 0, right? Because there is no change in the drain current. So it's going to be 0. So ACM is 0 and AD for the circuit is given by this. So if GM3 and GM1 are the same, what will be the gain in decibels? A differential gain in decibels. If GM3 and GM1 are same, what will be your gain in decibels? 0 dB, right? It's going to be 0 decibels. That's it. Okay, the next circuit. You're given a circuit of this type and you're supposed to find its differential gain. So to do that, first again, follow the same approach. So now, by now you're confident. Can I say that this node comes to differential ground? This node is already differential ground. So you don't even have to draw the half circuit and all of that. So you can directly say that this node will be at differential ground for M1. And on the upper side, you have two transistors. So you have one which is a diode connected transistor M3, and you also have another PMOS transistor in parallel. So I'm going to represent that PMOS transistor this way. Okay, we consider, yes. So now you are supposed to find the voltage gain here. Both the supplies are at AC ground. Now, can you tell me what will be the looking up resistance? So include R naughts as well. Include R naught of everything. Yes, no, you don't have to ignore. If you okay, first let's ignore R naught. Let's assume R naught is infinity for all the transistors. What will be the gain for the circuit? If you ignore R naught, what will be the gain of all the circuit? GM1 by GM3, you guys see that? See, you're looking into the PMOS, gate is at AC ground, source is at AC ground. So you're looking into the drain terminal. So the resistance offered by, if let's say this resistor had a finite R0, it would have been R0 phi. But since R0 is infinity, the resistance offered by the PMOS will be infinity as well. Okay, and similarly now you're looking into the source of M3. You're looking into the source of M3, gate is at ground, drain is also at AC ground. So the resistance will be 1 by GM3. So the gain will simply be GM1 by GM3. That will be the gain if you ignore R0, if you assume R0 is infinity. Now let's say you are considering R0, then what will be the gain? All devices R0 has to be considered. So first find the looking up resistance looking up into R3. If you look into R3, it's going to be 1 by GM3 in parallel with RO3 in parallel with RO5. So 1 by GM3 in parallel this, or down, looking down, it's going to be RO1. So this whole thing multiplied by GM1 will be your differential gain. Okay, the whole thing multiplied by GM1 will be your differential gain. No, the one of the questions is, if both MOSFETs are different, if both the MOSFETs are different, no, we can't use differential half circuit then. If the difference is negligibly small, then yes, we can. So with that's what we will be doing when we analyze non-idealities in the circuit, when mismatches and all that. But if they are way off, then you can't use differential half circuits. Okay, but we never do that. We don't choose the MOSFETs to be very different. Okay, so when you design differential pair, yes, generally that's the assumption. At least we'll ensure that this half is exactly the same as this half. This half is it. That's what you have to ensure. That's it. You don't have to necessarily ensure every MOSFET M3 and M1 are same. That you don't have to do. But you have to ensure the whole half. The half here should be same as this half. So which means M3 and M4, M5 and M6, they have to be similar. So if M5 was an NMOS, see here, the problem is you're looking into the drain terminal. We don't know, I'm not sure how you will connect an NMOS there. Okay, it's just adding one more NMOS in parallel if it is NMOS. But right now, I don't think that's an appropriate thing to say here. But if M5 was an NMOS, meaning it has to be connected in a certain way. So let's assume this is M5, this is VDD, and this is also connected this way. Yes, maybe it will be like that. It depends on what you connected the gate. Okay, yeah. But yes, if you're looking into the source, you will get 1 by GM5 parallel RO5. Yes. Yeah. Okay. So we'll analyze the next circuit. So this is the next circuit given to you. Your goal is, first step, the moment you see a circuit like this, you should automatically start drawing the So one of the questions is that, so why don't I answer it after the class? Okay, let me finish this question. I'll have to finish this. So we'll draw a small signal AC circuit. So can you tell me, if I draw, this is my axis of symmetry. Here in this circuit, you have to consider R0 and tell me. So you can ignore R0 first. First, let's ignore R0. Let's assume R0 is infinity. Can you tell me what is the gain of the circuit? Ignore R0. Ignore R0. See, look at where I have drawn a small signal line of symmetry here. GMR1, is that right? See, I can ignore R0 first. If I ignore R0, this node gate comes to AC ground, this node comes to AC ground, this node comes to AC ground. If all the three nodes comes to AC ground, then you'll see the circuit will reduce to something of this type. So you have 1 by GM, this is a AC ground, and you have a resistor R to AC ground. The PMOS will offer infinite resistance looking into the drain, so that doesn't matter. So therefore the gain will simply be GM1 R1. That will be the gain for the circuit. If you include R0, no, I'm finding the differential circuit. Generally the assumption is R1 is equal to R2. That's the differential circuit assumption. Okay, that's the differential circuit assumption. But yeah. So see, the whole idea is we are deriving everything from a half circuit, right? So it's assumed that it's symmetric. Yeah. Okay, so you have R1 equals to R2. So what we have here, the voltage gain is simply GM times R1. So now if you include R0, what do you think will be the difference in the gain? That's it, right? If you include R0, the only difference is you're going to get R03 in parallel. So you're going to get GM into R1 parallel R03. That's it. That's the only difference in the differential gain. Okay, that's it. So that finishes your differential circuit. So if you're given a circuit like this now, can you find the differential half circuit? So first you'll have to draw the line of symmetry. You have to draw the line of symmetry. Okay, sorry, I think one of you asked. Okay, I'm sorry. Yes, you have to consider. I'm sorry. So why is not R1 not considered? I'm sorry, that has to be considered. So your gain is actually R03 parallel R01. Yes, that's your exact expression for the gain. I was just telling you, if you just include R03, what would happen? That's it. Yes, this is the exact expression for the gain, because you have to consider the output resistance of NMOS as well. Now in the previous example, R1 and R2 were not different. They both have to be same. Otherwise you can't draw. See, look at it this way. You have R1 and R2. If this changes by delta V, this will changes by minus delta V. This node will come to AC ground only if R1 equals R2. If R1 is not equal to R2, this node will not come to AC ground, right? Differential ground. So we need that node to come to differential ground. Therefore, R1 has to be equal to R2. So only then I can approximate and find all this. Okay. So let me finish this question. So now, if you are given a circuit like this, so we just drew a half circuit this way. The line is here. If I draw a line here, what will happen? You'll have to split the resistor into two halves here, R by 2 and R by 2. So the half circuit, can I say, the half circuit reduces to something like this. So you have R by 2 here to ground, and then you have resistance R to AC ground. So what will be the differential gain for this circuit? Source is terminated with R by 2, so it will be GM into drain resistance. The GM reduces to GM by 1 plus GM R by 2 times the drain resistance, which is R here. That's it. So this is how you write the expression for differential gain in the circuit. Okay, so that's it. So we have analyzed this circuit reasonably well. And now can you tell me what will be the common mode gain for this circuit? follow the same approach. In common mode gain, what will be the common mode gain for the circuit? Look at it this way. You have here, you have a resistor R by 2 and R by 2. We are drawing the common mode half circuit. So this is R and this is R here. The common mode half circuit is, the common mode gain is 0, right? Because this node is open. This node is open here. If this node is open, then as far as small signal is concerned, the source is at 0, the source is at open circuit. So you have the drain current becomes 0. If the drain current is 0, then the voltage across the resistance will also be 0. Okay, so the common mode gain is 0 for the circuit. Okay, so we are done with some interesting questions on differential pairs, how to solve them using half circuit. Okay, so probably the next lecture we'll have a quiz. Okay, I'll stop at this